Dear students, in the previous class, I talked about the operators in quantum mechanics, the second postulates of quantum mechanics. And in operators of quantum mechanics, I said you that in quantum mechanics, for every physical variable, we have a corresponding operator. Okay? And that corresponding operators, when operated on a wave function, either changes the wave function or keeps the wave function same with multiplied by a particular constant. So, this is the behavior of an operator, and by which you can find out the value of the physical quantity for which of which the operator you are using. Okay. And I talked about the algebra of operator, addition and subtraction of operators, and then I talked about that multiplication of operators, what is null operator, what is unitary operator, all this we talked about in the previous class. Then I said you that in all the operators in quantum mechanics which we use is actually linear Hermitian operators. So, I defined the linear operators also, and I defined Hermitian operator also in the previous class. Okay. And linear operator and Hermitian operator, and all operators which we use in quantum mechanics are linear Hermitian operators. Okay. Then in Hermitian operators, I said you the definition, as well as I said you that if you are given a particular operator and you are asked to find out whether this operator is a Hermitian operator or not, then how to find out, this we did in the last class. And in doing this, we defined a dagger operator, which is a Hermitian, and in defining this, we talked about the adjoint of operator also. What is adjoint also? Adjoint of the matrix you have done in your mathematics, and so adjoints we have to find out that you take the transverse and then you take the conjugate. And in order to find out the adjoints of an operator, there are certain rules which we talked about, and using those rules I showed you that how you can talk about whether an operator is Hermitian or not. If A dagger is equal to A, then we say it is a Hermitian operator. If A dagger is equal to minus A, we say it is an anti-Hermitian operator. Okay. So, this is a Hermitian operator, and this is your anti-Hermitian operator. So, this we talked about in the previous class. Now, certain properties of Hermitian operators are very important, which you should know. So, I will talk about properties of Hermitian operator. And the first property is that summation or subtraction of Hermitian operators is always Hermitian. Okay, it's always Hermitian. It means that if you have an operator A and you take the dagger of A and is equal to A, if you take the dagger of B and is equal to A, then A and B, and then both A and B are Hermitian operators by definition. So, if you take the summation of the two operators A plus B and you take the dagger of this should be equal to A plus B. Then we say A plus B is a Hermitian operator. Or you take A minus B and you take the dagger of this, then this should be equal to A minus B, and this is a Hermitian operator. Okay. So, the first property is that if you sum two operators which are Hermitian, then the sum is also a Hermitian operator. If you subtract two operators which is Hermitian, then the subtracted operator is also the Hermitian operator. So, the first property is this one. Okay. So, the first property was that two operators A and B, which is Hermitian, if you sum it up and subtract it, then the summation or subtraction also becomes Hermitian. The second property is that multiplication of two Hermitian operator is only Hermitian when they commute. Means if you have two operators A, which is a Hermitian operator, B, which is a Hermitian operator, then we say that AB is a Hermitian operator, means AB becomes equal to AB only if A and B commute. What does it mean? AB commutator is equal to 0. And if you remember, I talked about yesterday that AB minus BA is the commutator, which we give a symbol like this one, AB. Okay. What about the two operators, say suppose X and Px? As we talked about yesterday, X is a position operator and Px is momentum operator, okay, and they do not commute, because if you find out the commutator x Px, it will not be equal to 0. What it will be? You can calculate, say first you find out x multiplied by Px. Px is what? Px is actually minus I h cross and d dx. So, you write x and then Px operator is minus I h cross d dx and add a function psi. So, x Px is x minus I h cross d dx of psi. This you have. Then you find out Px into x, and Px into x on a function okay. So, it will be minus I h cross d dx Px function, then x, which x operator is, let me give an operator symbol so that you do not get confused, okay. The operator is this one. Now, x is operator x is simply multiplication by x. So, multiply x with psi, and I said you that how do you operate? You operate from right to left. So, first you operate with x and then with d dx. So, a multiplication means it will be x psi. Now, you have two different terms 1 and 2. So, you differentiate it, minus I h cross you take it outside, and if you differentiate it, then what do you get? You get psi and then plus, then you keep your psi constant and differentiation to x will give you this one, and keep x constant and differentiate with psi. So, you get this one. So, what you have minus I h cross psi and minus I h cross x d psi by dx. Okay. So, you take this and now you find out x Px minus Px into x, minus Px into x, that is the commutator. So, it will be what? X Px is minus I h cross x d psi by dx, this is your x Px, and Px is this one. So, it will be minus plus I h cross psi, and then again minus plus I h cross x d psi by dx. So, these two will go and you will have plus I h cross into psi. So, the commutator for x p x is not equal to 0, commutator for x p x is actually equal to I h cross. They do not commute. Position and momentum operator do not commute. I talked about this yesterday also. Okay. But in contrast to this, so what does it mean? It means x p x commutator x p x will not be a Hermitian operator. If they commute, then only it will be a Hermitian operator. So, x p x x into p x is not a Hermitian operator. Okay. Then what the third property is that commutators of two Hermitian operator is anti-Hermitian. Okay. Means if you have A dagger is equal to A, B dagger is equal to B and AB is the commutator. Okay. So, that AB dagger BA dagger or AB dagger minus BA dagger, then we say B dagger A dagger minus A dagger B dagger AB minus BA, this is equal to AB. So, it is an anti-Hermitian. Commutator of two Hermitian operators is anti-Hermitian. It means x p x commutator dagger should be equal to minus x p x. Okay. Okay. So, commutator of two Hermitian operators is anti-Hermitian, means x p x is dagger of x p x is minus x into p x. So, this is the third property of operators. Okay. Now, next property of operators. Next property, fourth one, is that anti-commutator of two Hermitian operator operators, anti-commutator of two Hermitian operator is Hermitian. Okay. What does that mean? A B is the commutator and A B anti-commutator two Hermitian operators is equal to 0. Okay. So, this we say is anti-commutator. Two Hermitian operator is operator. Again, what does it mean? That anti-commutator is A, B, I have given a positive sign here. So, dagger of this should be equal to A, B of this one. Then only it will be Hermitian, otherwise it will be not. Okay. Then the most important property for which we use Hermitian operator in quantum mechanics is that eigenvalue of a Hermitian operator is always real. Always real. and you need real eigenvalues, means if you have a is equal to A, and if you have to find out, if you operate with this operator and if you get it like this one ASI, okay, then what, how will you write this Hermitian condition? If you write Hermitian condition like this, psi star A psi d tau is equal to how much, what? Change the position of first with third and then you write d tau. Okay. So, this is the Hermitian condition. Hermitian condition which we talked about. Okay. And if we move with this Hermitian condition, again I am writing psi star A psi d tau becomes equal to psi A star psi star d tau. What is A psi? A, when you operate with this one, you get A psi d tau, and if you operate with this one, A star psi star d tau, and this you can write is A psi star psi d tau A star psi star d tau. So, what does it mean? Complex conjugate is same, and this means A is real, then only conjugate and both will be same. Okay. So, the most important property of Hermitian operator is that it always gives real eigenvalues. Okay. And then the last one is that non-degenerate eigenfunctions corresponding to Hermitian operators are orthogonal. Non-degenerate eigenfunctions of corresponding Hermitian operators are orthogonal. What does it mean? It means that if you operate with an operator on a function psi m, so that you get A m psi m, and if you operate with the same operator on a different wave function psi n, and you get A n psi n, A m is equal to A n, then it is degenerate. Then it is degenerate. A m is not equal to A n, then it is non-degenerate. We will talk about this in details later on. Okay. And if it is a non-degenerate, then psi m psi n d tau is equal to 0. Okay. So that they are orthogonal. With these properties of operators, we end the postulate number 2 and we go to postulate number 3. So, the postulate 3 is about the eigenvalue and eigenfunctions. Eigenvalue and eigenfunctions. I said you that when you operate with an operator on a function, means you use an operator, operate on a wave function, then you may get the same wave function multiplied by a constant. And if it is so that you get a constant multiplied by the same wave function, so now I write operator OP on a function psi, giving you a constant a multiplied by psi, then this particular equation is called eigenvalue equation. Eigenvalue equation. These functions are called eigenfunction, and this constant value is called eigenvalue. One of the example of this we have already done. What we write Schrodinger wave equation? We write H psi is equal to E psi, where H is Hamiltonian operator, which is operator for energy, and what is this? This is energy, and this psi is called eigenfunction. So, H psi is equal to E psi is actually an eigenvalue equation, where psi is an eigenfunction and E is the eigenvalue. The constant gives, and in this way, for any physical quantity you use an operator, operate with the operator on the function, and you get a constant value, and that constant value is the value of the physical variable whose operator you are using. Okay. Say for example, if you use p x on a function psi and you get some value c and p x back, then this c is the numerical value of x component of momentum. Okay. If you use a position operator, operate with this and you get a value, say for example d into psi, then d is the numerical value of position. But you will not get always this case. You can operate with an operator on a wave function and you wave function not the same wave function. You may have a constant, you may not have a constant, and certain value. Okay. So, in this case, this wave function is not an eigenfunction. This is not eigenvalue. Okay. So, whenever you operate with an operator on a function and you get the function back along with the constant, then you say it is an eigenvalue equation. Otherwise, so operator when operated on an eigenfunction means you get the same eigenfunction back here multiplied by a constant, and this is called, I hope now you understand, this is what is eigenvalue equation. Okay. Now, for example, say suppose your operator is d dx. I said your operator is a mathematical symbol, so it is a differentiation, and your function is exponential a x. So, what will happen? Try to operate it, d dx exponential a x. What do you get? You get a into exponential a x. So, you get the same function back with a constant value, and we say that exponential a x is an eigenfunction of eigenfunction of operator d dx for which the eigenvalue is A. Okay. So, now hope it is clear that you must get the same function. What does it mean? It means that you can operate with an operator on any wave function, but that wave function may not be an eigenfunction. Your wave function may change when you operate with an operator, and if it changes, then it is not an eigenfunction. If it does not changes and it gives you a constant multiplied by the same function, then only it is an eigenfunction. So, all eigenfunctions are wave functions, but all wave functions are not eigenfunctions. They may be, they may not be. Let us see another example. So, for example, your operator remains same d dx. I am changing the function. The function psi becomes equal to exponential minus a, or not minus, a x square. What will happen now? If you operate with an operator exponential a x square, then what do you get? You get 2 a x exponential a x square. Now, you see your constant value is 2 a and your function is, though you get e exponential a x square back, but you do have the variable x also, which is not a constant. So, your variable should not be here, and now the new function is this one. This is the new function, which is not the same function, a different function. Okay. So, we will say that exponential a x square is not an eigenfunction of d dx. So, there is no question of eigenvalue. If it does not give you the same function, then there is no question of eigenvalue. See some more examples. Okay. So, another example is that operator is d square by dx square, and your function is cos 4x. Suppose this is your function. What will happen? You will operate with the operator on cos 4x. What do you get? You get d dx, and one time operation means minus 4 sin 4x, and again you operate with this one, it will be minus 16 cos 4x. So, when you operate with, means if you double differentiate cos 4x, what you get is minus 16 cos 4x. Look at this function, look at this function. You have the same function here, cos 4x, cos 4x. So, the eigenvalue is minus 16 and cos 4x is an eigenfunction. This way you can see about different functions, that whether they are the eigenvalue or not. Let us see. Try another function, say exponential minus I 4x, okay, and use two operators d dx and d square by dx square, and check whether they are eigenfunctions or not. So, d dx of minus exponential minus I 4x will be what? It will be minus I 4 into exponential minus I 4x. This you can write. Okay. So, what does it mean? It means you get the function back. If you square d square by dx square of exponential minus I 4x, then it will be again minus I 4 and again minus I 4 exponential minus I 4x, and it will be minus minus plus I square will be again minus. So, minus 16 exponential minus I 4x. Okay. So, here you have, this is the constant value minus 16. So, this will give you, this is again an eigenfunction for d square by dx square. Okay. Now, if I say that a wave function psi is represented by minus I 4x, then I say find out the value of p x, find the value of x component of momentum. Then what is this? Minus I h cross d dx, and you have the function like this one. So, one time differentiation you will do, and what you will get? Minus I h cross, then minus I 4 and exponential minus I 4x. So, it will be minus 4 h cross exponential minus I 4x. Okay. So, minus 4 h cross is the value of x component of momentum. Okay. So, the third postulate is eigenvalue equation, where you operate with an operator on a function and you get a constant multiplied by the same function. That constant is the value of the physical variable whose operator has been used. Okay. If you use a Hamiltonian operator on a wave function psi, which is an eigenfunction, then you get energy and the same function back. If you operate with linear momentum operator, you get the value of p into psi. If you operate with position operator on a function psi and you get some constant into phi, then this is the value of position. So, this is the numerical value of position. This is the numerical value of momentum, this is the numerical value of energy. Provided if psi is an eigenfunction. Okay. So, in quantum mechanics, I said you that the basic idea is to find out the wave function for a particular system, and once you find out the wave function, then you, in order to ensure that the particle is within the boundary, you normalize it. I talked about the normalization procedure also. Then the next task is of finding out the physical variables of the system, knowing the properties of the system, what is its position, what is its velocity, what is its momentum, what is its energy, everything you want to find out. And for that we have an operator formalism, that for every physical variable we have a particular operators, and these operators are mathematical, a symbol for mathematical operation, with which if you operate on a function and if you get the function back along with a constant, then that constant is the value of the physical variable whose operator you are using. Here you are using an operator for energy, so you get the energy value. You are using an operator for momentum, so you get the momentum value. You are using an operator for position, so you get the position value. Okay. So, this is the third postulate, and we are left with two small postulates. We will talk about this in the next class, as well as we will try to apply the Schrodinger wave equation to simple systems in the next class also. Thank you.